Heat is the form of energy that is transferred between two substances at different temperatures. The direction of energy flow is from the substance of higher temperature to the substance of lower temperature. Heat is measured in units of energy, usually calories or joules. Heat and temperature are often used interchangeably, but this is incorrect. Temperature is the measure of hotness or coldness of matter. Stated another way, temperature is the average kinetic energy per molecule of a substance. Temperature is measured in degrees on the Celsius, C, or Fahrenheit, F scale, or in kelvins, K. In simplest terms, temperature is how hot or cold an object is, while heat is the energy that flows from a hotter object to a cooler one. For example, the temperature of a cup of coffee may feel hot if you put your hand around it. It is hot because heat from the coffee is transferred to the cup. Thermal expansion is a phenomenon that takes place in solids, liquids, and gases. Almost all substances expand when their temperatures increase unless they are constrained in some manner. Examples include the heating of air in a hot air balloon, which makes the balloon expand and rise, and mercury in a thermometer, which rises in response to heat. Metal rods are used in a variety of applications also. For example, metal rods or strips that are used as expansion joints at the ends of bridge sections account for the expansion of steel bridges in hotter weather. The amount of expansion that occurs and how we predict it depends on the substance. For example, a solid metal rod generally expands linearly and increases in length, while liquids and gases experience an increase in volume. In all three cases, thermal expansion occurs in response to an increase in temperature, and useful devices take advantage of this concept. Thermodynamics is the study of heat and its transformation to mechanical energy. There are 4 laws of thermodynamics, but we only concentrate on the 2 principal laws here, the first law and the second law. The first law says that the change in internal energy of a substance equals the work done on it plus the heat transferred to it. Mathematically, we use the equation delta U equals work plus Q. Internal energy is the sum of the kinetic and potential energies of all the atoms and molecules within a substance. The significance of the first law of thermodynamics is that there are 2 ways to increase the temperature of a substance. 1, by exposing it to another substance that has a higher temperature, and 2, by doing certain kinds of work on the substance. Friction and compression of gases are 2 examples of ways to increase temperature by the work method. Pistons in internal combustion engines take advantage of this concept. Air is compressed in a cylinder by the piston, which raises the temperature to almost 27 times the temperature of the uncompressed state. The second law says that heat cannot be transferred from a colder body to a hotter body without work being done by an outside agent. Stated another way, no device can be built that will repeatedly extract heat from a source and deliver mechanical energy without ejecting some heat to a lower temperature reservoir. The perfect example is the heat engine, which is discussed later in the lesson. Heat transfer occurs by 3 mechanisms: conduction, convection, and radiation. Conduction is the transfer of heat between atoms and molecules in direct contact. Convection is the transfer of heat by movement of the heated substance itself, such as by currents in a fluid. Radiation is the transfer of heat by way of electromagnetic waves. An example of conduction is heating up a pot of water on an electric stove. The bottom of the pan is in contact with the hot stovetop. Heat flows from the burner to the bottom of the pan and even up the sides and possibly to the handle. Conduction also occurs between the pan and the water, which are also in contact with each other. An example of convection is a forced air heating system. Warm air is blown and mixed with cooler air to cause heating of the cooler air by the warmer air. An example of heat transfer by radiation is the sun, or a hot fire. The sun radiates electromagnetic waves that heat the earth, as does a fire that heats your hands or body when you move near it. Combinations of these mechanisms are also used. An example is the heating of a home that uses all 3 principles. Using insulation in the house actually reduces the conduction of heat from hot surfaces inside the house to the colder surfaces outside. A forced air system, along with allowing sunlight into the house, can be used inside as well. The specific heat capacity, or just specific heat, is the quantity of heat required to raise the temperature of a unit mass, e.g. 1 gram, 1 kilogram, etc., of a substance by 1 degree Celsius. The specific heat of pure water is 4,180 joules per kilogram degree Celsius, which means 4,180 joules of energy are required to raise the temperature of 1 kilogram of pure water 1 degree Celsius. Practical uses for specific heat itself are sparse, so it is usually used to calculate other quantities. One comparison of different specific heats is that the energy needed to heat 5 cups of water to boiling is about the same as the energy needed to accelerate a small car to 60 miles per hour. A heat engine is a device that transforms heat into mechanical energy. It absorbs heat from a hot source, such as burning fuel, converts some of this energy into usable mechanical energy, and outputs the remaining energy as heat to some lower temperature reservoir. The heat engine is the implementation of the second law of thermodynamics. Fossil fuels, such as coal, oil, and natural gas, are usually used as the energy input for heat engines. Gasoline, diesel, and jet engines, as well as coal-fired power plants, are examples of heat engines. According to the second law, not all of the energy input into a heat engine is converted into usable mechanical work. Stated another way, no device can convert 100% of the input heat into mechanical energy. Therefore, a heat engine has a certain efficiency, which describes how much of the heat it can convert into a usable output. Mathematically, the formula is efficiency equals energy output over energy input times 100. For example, if a device is 50% efficient, it converts half of the input energy into mechanical energy, and the other half is wasted. The maximum efficiency of a heat engine, which is called the Carnot efficiency, after the French engineer Sadi Carnot, depends on the temperatures of the heat source and of the lower temperature reservoir. Heat and temperature are often used interchangeably, but are actually two different things. Heat is the energy that is transferred from two substances at different temperatures and flows from hot to cold. Temperature is a measure of how hot or cold a substance is. This lesson also explored several practical applications of heat, including thermal expansion, the first and second laws of thermodynamics, heat transfer, specific heat, and heat engines.